Welcome. We are doing another division proof. This time we're going to look at whether 5 divides n to the fifth minus n when n is a non-negative integer, and we'll prove this by induction. This is from Discrete Mathematics and its application, 7th edition by Kenneth Rosen. I am using the 7th edition, so the problem comes from chapter 5.1, question number 33. If you're using a different edition, this might be a different problem or chapter for you, but nevertheless, it should be in whatever edition you're using. So we're going to prove by induction that 5 divides n to the fifth minus n. We've done a few of these videos of division. So let's talk first about what it means to divide. So integer division, let's say x divides y. This vertical line means divides. So when we say that two integers, one divides the other for some integer xy, let me write that over here. Fancy z is the set of integers. This means it divides it evenly. And it also means that I can write y as an integer multiple of x. So division means I can write y as some value x times some integer k. So this is what it means to divide. Let's look at an obvious example. 3 divides 6. This, of course, means I can write 3 as some integer multiple of 6. We know k here is 2, so 3 times 2 equals 6. We could also say something like 3 divides x. That would mean that we can write x as a multiple of 3. Now, I'm using k here just as a choice. You can use whatever variable you want for the integer. But this is what integer division means. And so when we are proving that 5 divides n to the fifth minus n, what we want to show is that n to the fifth minus n is equal to some integer multiple of 5. So in other words, if we do this correctly, at the end, we should have n to the fifth minus n is equal to 5 times some integer. So let's begin. Let's look at the base case. In these videos, especially with induction proofs, I like to spell everything out, go step by step. Your proofs might be a little different where you don't write as much as me, but I am really trying to illustrate as much detail as possible. And so we are asked to prove this for integers, non-negative integers, which is essentially for all n greater than or equal to 0. So the base case here is n is equal to 0, or p of 0. And so let's look at n to the fifth minus n. That's 5 to the 0 minus 0. 0 minus 0 equals 0. And of course, 5 divides 0 because everything divides 0. So just for an argument's sake, let's look at some other cases just to get a sense of what's happening. Let's look at n equals 1. Well, that's 1 to the fifth minus 1, which is 1 minus 1, which is 0. And again, everything divides 0, so 5 divides 0. Perhaps more interesting is if n is 2, then we have 2 to the fifth minus 2 is equal to 32 minus 2, which is equal to 30. And 5 divides 30. Okay, so you only need to show the base case that n equals 0 is true. But just to illustrate what was happening, we went through n1 and n2. So the base case holds. Again, you don't have to write this. Now, let's talk about the inductive step. So the inductive step here is we're first going to establish the induction hypothesis was the assumption that 5 will divide k to the fifth minus k. We're replacing n with some integer k. variable. So let's write that. Assume that 5 divides k to the 5th minus k, or k greater than or equal to 0. Now, again, the assumption is that this is true, and this is what we call the induction hypothesis. I like to put IH next to the induction hypothesis. Again, just so I can look back and see when I used it. As I said in other videos, if you get through an induction proof and you haven't used the induction hypothesis, odds are that you probably did use the induction hypothesis, or maybe you made some other assumption that you shouldn't have, but you should always go back and look to see that you use the induction hypothesis. All right, so what is it we want to do here? Well, we said that at the beginning, so let's write it. We want to show that the k plus 1 case holds. In other words, pk plus 1. And the induction hypothesis is pk essentially, right? It's that we're assuming it up to k. So here we want to show that the pk k plus 1 case holds. And so what is that literally? Well, we're going to take the induction hypothesis and we're going to replace k with k plus 1. So what we want to show is that 5 divides I'm going to put a question mark, and I'm replacing k in the induction hypothesis was k plus 1, so k plus 1 to the 5th minus k plus 1. This is what we want to show. We want to show that the next case, k plus 1 case, holds. And essentially, k plus 1 to the 5th minus k plus 1 is divisible by 5. With most induction proofs, we're going to look at this algebraically and make an argument of why this k plus 1 to the 5th minus k plus 1 is divisible by 5. So let's look at this. So what this means literally is that I'm taking k plus 1 and I'm multiplying it by itself 5 times. That was minus k plus 1. Now, we've done a video where we explain how to multiply polynomials using FOIL distribution. You can review that. I'll put a link in the description. But here I want to introduce something that we haven't used in any of our induction proofs yet. That is a very handy tool. So you can skip ahead if you don't want to look at this part, but this is useful when you have polynomials like this that are a degree that is somewhat unmanageable. Like if we were to multiply this out, it would suck. It would be a lot of work and be a long chain of polynomials. Now, what I'm about to do might not look like it's any easier, but when you get the hang of this, it's fairly straightforward. So as an aside, we're going to talk about something called the binomial theorem. And binomial theorem, like I said, once you get used to it, is a really easy way, one of them at least, to multiply binomials. In this case, k plus 1 to the 5th, we want to multiply. So the binomial theorem says that if I have a plus b raised to some power of n, this will equal the sum, that's sigma, from k to 0 to n of the combination of nk and then a, n minus k, b to the k. Now, again, that does not look easier than what I was suggesting. But again, if you look, it gets a little bit easier. So this is the nk part is the coefficient of the binomial. And if you've taken probability or in your discrete class, you might have talked about this a little bit. This is sort of n choose k. And the way we think of n choose k, there's a formula. It's n factorial divided by k factorial n minus k factorial. So that's what this part is. A and B are obvious from the binomial we've chosen. 0 to n, in our case, it would be n would be 5, and then we would sum from 0 to 5. So in the future, I will produce a binomial theorem video. Which I will link when I have that ready. But for now, let's just look at our particular problem and then work through the binomial theorem. Again, it's not going to look that much easier than what we're trying to accomplish, but trust me that it is once you get comfortable. So what we have, I'm going to use x's just so I don't confuse the situation. So we have essentially x plus 1 to the 5th. And instead of multiplying that, which again will suck, we want to write this using the binomial theorem. So we know that this is going to be a sum from k equals 0 to 5. And we have nk, so n here is 5, k. And then we have x essentially to the 5 minus k. Now, where's the other part? Well, b is 1. So anything raised to 1 will just be 1. So essentially, we'd have 1 raised to k. But again, since 1 raised to any power is 1, we could sort of admit that. So if we write out some of the terms of this, not some, we'll write out all of the terms. We could look at what this is. So we start with k is 0. So we have 5 choose 0, x to the 5 minus 0, which is 5. Again, I'm going to omit the 1 just so notationally it doesn't get unruly. Then we have 5 to the 1 because that's the next term. Then x 5 minus 1. Then plus 5, 2. That's x to the 5 minus 2 plus 5 choose 3, x to the 5 minus 3. I'm going to move this down. 5 choose 4, x to the 5 minus 4, plus 5 choose 5, x to the 5 minus 5. So we have 5, 0. I'll write that better. 5, 0, x to the 5th, plus 5 choose 1, x to the 4th, plus 5 choose 2, x to the 3rd, plus 5 choose 3, x to the 2, plus 5 choose 4, x plus 5 choose 5. All right, so that's our polynomial when we multiply out x plus 1 to the 5th. Now, each of these, remember, the form says this is 5 factorial divided by 0 factorial, 5 minus 0 factorial. And so what is that? Well, it's essentially 5 factorial over 5 factorial, which is 1. So the coefficient of x to the 5th is 1. Let's do 5. So let me write this here. 5, 0 is this. 5 choose 1 then is going to be 5 factorial, 1 factorial. 5 minus 1 is 4 factorial. This is 5 factorial divided by 4 factorial, which is 5 times 4 times 3 times 2 times 1. This is 4 times 3 times 2 times 1. So we can cancel this, and we get 5. Again, this not looking like it's easier, but bear with it. Let's look at what 5 and 5 are. 5 choose 5 is going to be 5 factorial over 5. 5 minus 0 is, 5 minus 5 rather is 0 factorial, and that's just 5 factorial over 5 factorial is 1. So notice here that 5 choose 0 is going to be the same as 5 choose 5. Now notice also that in this binomial theorem, this will always be true of the first and last terms. So you can see now we're saving some time, right? All right, so 5 choose 1 is 5. What about 5 choose 4? So I'm skipping around a little. That's 5 factorial, 4 factorial, 1 factorial, which is the same as 5 choose 1, which is 5. So 5 choose 1, 5 choose 4, 5 choose 5, 5 choose 0. Really, it's only have to do 2 of these. So this is the same as 5 choose 4. And I'll put this together at the end so we have something. So 5 choose 2 is 5 factorial divided by 2 factorial. 5 minus 2 is 3 factorial. When we do the cancellation, I'll write it out literally. And I'm just going to write 2, and then we have 3 times 2 times 1. So this cancels. Now 5 times 4 is 20 divided by 2 factorial, which is 2. So that's 10. What about 5 choose 3? Well, that's 5 factorial, 3 factorial. 5 minus 3 is 2 factorial, which is the same as 5 choose 2. So this is also 10. So that's it, right? So you can see they sort of pair up depending. So x plus 1 to the 5th is equal to, using binomial theorem, k to the 0 to 5. 5 choose k of x. Now we had, recall, we had 1, but we're not going to write it. 5 minus k, which is, if we substitute what we have for the combinations, then we have k to the 5th because it had factor of 1. Then the next one was 5, k to the 4th. I'm using k's in place of x's here. Maybe I should keep the x's, and then I'll replace it at the end. So x to the 5th plus 5x to the 4th plus 10x to the 3rd plus 10x squared plus 5x plus 1. Now, in the separate video I'll do for the binomial theorem, we'll talk about Pascal's triangle, which is an extreme shortcut to this based upon summing in a triangle. That's a little out of the scope of this video, so look for that. So this is our polynomial. Now I'm going to replace it because we had k plus 1 to the 5th, and that was now k to the 5th minus 5k to the 5th, or 4th, sorry, plus 10k to the 3rd plus 10k squared plus 5k plus 1. So let's put this together with what we had. That was k to the 5th plus 5k to the 4th plus 10k to the 3rd plus 10k squared plus 5k plus 1 minus, we had k plus 1. So minus k minus 1. So let's think about the side being over. So we're back to our induction problem. So if you skipped to this part, this is a continuation of the induction proof, just going through the algebra. This is our polynomial. Now, usually at this stage, you want to group like terms and start to minimize, simplify, factor, all that lovely stuff. But let's resist. resist doing that, resist doing the obvious algebra, because we want to use the induction hypothesis. Now, the induction hypothesis said that 5 divides k to the 5th minus k. So what I'm going to do is I'm going to group from this long polynomial k to the 5th minus k, which means I'm taking this term and this term, and I'm going to group the rest of it. So we have 5k to the 4th, we have 10k to the 3rd, we have 10k squared, we have 5k. Now 1 minus 1 is just 0, so this is the polynomial. Okay, so by the induction hypothesis, again, 5 divides k to the 5th minus k, which means that we can write k to the 5th minus k as an integer multiple of 5. So by the induction hypothesis, 5 divides k to the 5th minus k. So we can write that k to the 5th minus k as some integer multiple of 5. Let's call it 5 m. So m is some integer. Now we can replace this. So replace in our equation here. So we get 5 to the m. So we're replacing k to the 5th minus k. Now here we see we can factor out a 5. That leaves us with k to the 4th plus 2k to the 3rd plus 2k squared plus k. All right, so all I did there was factor out a 5. If you need some help factoring, we have a video lecture on factoring for college algebra review. Check that out. All right, so what is this guy? Well, the sum and difference of integers is an integer, and multiplying integers also results in an integer. So this is just an integer. Let's say we named it. Again, these are steps you don't necessarily need to do. At this point, you could have just made the argument, but I'm trying to be thorough. So let's say this is equal to, let's say, p. And we'll substitute that, and p is an integer. If we didn't get an integer, we'd be in trouble, right? Because we were trying to show that it's divisible by 5. And if it's not an integer, then the integer theorem of integers, or the division theorem of integers does not hold. Now I'm factoring a 5 from this. And so we see that's 5 times some integer. So it's an integer multiple of 5. So what does this mean? Well, it means that k plus 1 to the 5th minus k plus 1 is equal to 5 times m plus p, which means that it's an integer multiple. So that means 5 divides, this is exactly what we wanted, k plus 1 to the 5th minus k plus 1. And that's it. That's the end of the proof. QED, I like the box. So that's the end of the proof. We've just proven that 5 divides n to the 5th minus n for all n greater than or equal to 0, with a long explanation of binomial theorem in the middle. So look for the binomial theorem video coming soon. And that's it. Thank you for watching. Like and subscribe, and check out our other induction proof videos, and have a great day.